Unit 4 Chemistry, Chapter 11, Part 4. Looking here at reaction pathways. But first we do have one more reaction of functional groups, which is the formation of an amide. Okay. So, just as between an alkanol and a carboxylic acid we can make an ester by a condensation reaction which produces water, if we have a carboxylic acid and an amine, then we can also do a condensation reaction to produce water. And in this case, we're going to make an amide. Okay, here's our amide functional group, all four of those atoms, which are linked together. And what we did was we lost the OH group here, and we lost a hydrogen from there. Now, we can link all these reaction types together to make a reaction pathway. A reaction pathway is a series of reactions, one after the other, that is used to make a particular chemical that you are desiring. Okay? So, for instance, you might start with an alkane, and you might be wanting to make a ketone. You can't do that directly. What you can do is you can turn it first into a haloalkane. So you could react with Cl2, for instance, and you could therefore add a chloro group. You can then substitute that chloro group for an alkanol group, and you could then oxidize it in order to make a ketone. Of course, here we've made a secondary alcohol, which is why we're making a ketone rather than an aldehyde or a carboxylic acid. Okay? You know all of these steps individually, so now it's about putting these steps together to have the overall pathway to make the molecule that you are desiring. A couple of important things that you'll need to calculate here. The first is atom economy. Now, atom economy is very useful because it measures what proportion of the total matter you started with ended up in your useful product as opposed to your waste products. Simple calculation, you find the molar mass of your useful product, divide it by the molar mass of all products, and times by 100. Sometimes you'll see this saying as it's divided by the molar mass of all reactants. It's the same thing. Okay? Matter is not created or destroyed in a chemical reaction, so the total molar mass of all products and all reactants has to be equal. Okay? So don't worry if you see this written in a slightly different way, it means the same thing. So if, for instance, we had a substitution reaction where we are substituting a chloroalkane, in this case chloroethane, and we're going to substitute it for this OH group, okay, because we want an alkanol. This here is our useful product, which has a molar mass of 46 grams per mole. This is our byproduct, which has got a molar mass of 56 grams per mole. I'm going to take the molar mass of my useful product, divide it by the total molar mass, times by 100, and that gives me an atom economy of 44%. Just one important thing here. Coefficients are going to be important. Now, this is a 1 to 1 to 1 ratio. But if it was a 2 to 1 ratio, then I would multiply this molar mass by 2 before I put it into my equation. The other thing you might be asked to calculate is percentage yield. Now that's a way of measuring what proportion of the reactants you started with actually turned into the products. Yeah? You'll remember this from equilibrium, that not all of your reactants turn into your products. Again, it's a nice simple calculation because it's a percentage. It's your actual product divided by your theoretical times 100. So if we had an esterification and we had 0.1 mole of a methanol reacting with 0.23 moles of ethanoic acid, and we find out that we make 5.3 grams of the ester. 1 to 1 ratio, so we know our methanol is limiting. Okay, we need to find out what our theoretical product yield is. So we do, the mass is going to be equal to the amount in mole of the ester we're going to make times the molar mass, okay, which is the same as the molar mass of the methanol because it's our limiting reagent and because it's a 1 to 1 ratio in our equation. So theoretically we could make 7.4 grams. Our percentage yield then would be 5.3 over 7.4 times 100, so we got a 72% yield, which is pretty good actually.